What if everything you see, the stars, the galaxies, the light in the night sky, is only a small part of what actually exists? What if most of the universe is invisible? Right now, something unseen is moving through you, through Earth, through the entire galaxy. It doesn't glow. It doesn't make sound. But without it, galaxies would fall apart, and you might never have existed. Scientists call it dark matter. We can't see. It can't touch it, but gravity proves it's there. This is the story of the greatest cosmic hunt in human historia. Hunt for something that refuses to be seen, but controls the universe anyway. Right now, in this very moment, you are surrounded by something you cannot see. Not air, not darkness, not empty space. Something else. Something that does not glow, does not reflect, does not block light. Something that passes through your body as easily as sunlight passes through glass. Something that fills the universe quietly, invisibly. Relentlessly, scientists call it dark matter. And even though you've never seen it, touched it, or photographed it, without it, nothing you know would exist. No galaxies, no stars, no planets, no Earth, no you. Every atom in your body, every breath you take exists because of forces shaped by something that refuses to show its face. We live in a universe where what we see is not what truly dominates, where light is only a surface layer floating on top of a much deeper, darker structure, where most of reality is hidden and only gravity whispers its presence. This is not science fiction. This is not philosophy. This is physics at its most unsettling. Because when scientists add up everything, we can see every star, every galaxy, every cloud of gas, every planet. They get a shocking answer. All visible matter in the universe makes up less than 1/5 of what must exist. That means more than 80% of the universe's matter is invisible. Not missing, not lost, but unseen. And the only reason we know it's there is because without it, the universe would tear itself apart. Imagine throwing a stone tied to a string. The string is what keeps the stone from flying away. Gravity is the string of the cosmos. But when scientists measured how fast galaxies spin, how clusters move, how light bends across space, they realized something terrifying. The visible string is far too weak. Galaxies spin so fast, they should rip themselves apart. Clusters of galaxies move so violently, they should scatter into nothingness. Light bends around places where no visible mass exists. Something invisible is pulling. Something unseen is holding. Something dark is shaping everything. And that realization changed science forever. The hunt for dark matter didn't begin with advanced machines or massive laboratories. It began with a simple question: why is the universe still holding together? In the 1930s, an astronomer named Fritz Zwicky studied a massive group of galaxies called the Coma Cluster. He measured how fast those galaxies were moving around each other. What he found made no sense. They were moving too fast. According to known physics, the visible matter in that cluster did not have enough gravity to hold it together. The galaxies should have flown apart billions of years ago, but they didn't. They stayed bound, locked together by something unseen. Zwicky concluded that there must be hidden mass, something he could not see but could measure through its cuts: gravitational pull. He called it Dunkel Materie. Dark matter. At first, almost nobody believed him. The idea sounded like a patch, a guess, a way to save broken equations. Science prefers explanations you can test, touch, and observe. And dark matter was none of those. So for decades, the idea waited in the shadows, barely noticed, until the universe itself refused to stay quiet in the 1970s. Another scientist, Vera Rubin, studied how stars move inside spiral galaxies. She expected a familiar pattern. Stars closer to the center move faster. Stars farther away move slower, just like planets around the sun. But what she found was deeply disturbing. Stars at the outer edges of galaxies were moving just as fast as stars near the center, according to gravity. They should have been flung into space, yet they stayed in orbit as if held by an invisible hand, again and again. Galaxy after galaxy showed the same impossible pattern. Rubin didn't invent dark matter. She revealed that it could no longer be ignored. Something unseen surrounded galaxies like a massive halo. Something heavy, silent, and invisible was controlling their motion. From that moment on, dark matter was no longer optional. It became necessary. But here's what makes this story strange. We still don't know what dark matter is. We know what it does. We know how much of it there must be. We know where it gathers, but we don't know its true nature. It is not dark clouds, not hidden stars, not black holes, not gas or dust. We can detect all of those. Dark matter does not emit light. It does not absorb light. It does not block. Light passes through it as if nothing is there. Right now, trillions of dark matter particles, if they are particles, are passing through your body every second. They go through your skin, your bones, your brain, your heart, and out the other side, without leaving a trace. They don't care about walls. They don't care about steel. They don't care about you. The only thing they care about is gravity. Dark matter pulls. It shapes. It organizes. It bends the paths of stars. It decides where galaxies are born. It builds the large-scale structure of the universe on the biggest scales. The universe looks like a giant web, filaments of galaxies stretching across space, separated by vast, empty voids. This is called the cosmic web, and dark matter is its skeleton. Simulations show that dark matter clumps first. Then normal matter, gas, dust, stars falls into those gravitational valleys. Galaxies form where dark matter already waits. In other words, we don't build galaxies, dark matter builds galaxies. We just light them up. One of the strangest tools in this hunt is something called gravitational lensing. When light from a distant galaxy passes near a massive object, gravity bends the light, just like a lens bends glass. The background galaxy appears stretched, curved, or duplicated by measuring this distortion. Scientists can map gravity itself, and when they do, they often find more mass than they can see in galaxy clusters. Gravitational maps reveal giant invisible shapes, clouds of mass with no light, no stars, no gas. Just gravity. Dark matter drawn in pure mathematics. It is there, it is massive, it is unavoidable, so what is it? Some scientists believe dark matter is made of new particles that barely interact with normal matter. One popular idea is WIMPs, weakly interacting massive particles. Heavy, slow-moving particles that pass through everything. Another idea is ixions, extremely light particles that behave strangely in magnetic fields. Others suggest exotic particles from extra dimensions, or sterile neutrinos that barely touch our world. And some ask an even more dangerous question. What if dark matter isn't matter at all? What if gravity itself changes on large scales? What if our equations are wrong? So far, dark matter explains more evidence more cleanly. But science never closes the door. It only follows the strongest trail to catch dark matter. Scientists have built detectors deep underground, under mountains, inside mines, beneath the Earth itself. These places are quiet, shielded from cosmic noise. They wait for the smallest sign, a single collision between dark matter and an atom. So far, nothing, no confirmed hit, no undeniable signal. But every failure narrows the possibilities. Other experiments look to space. They search for flashes of gamma rays that could appear when dark matter particles collide with each other. Telescopes like Hubble and James Webb map dark matter by watching how it bends light. Every distorted galaxy is a clue. Every curved beam of light is a fingerprint. Slowly, we are drawing a map of an invisible universe, and here's what makes this story deeply human. Dark matter is not just about particles and equations. It is about origin. Dark matter decided where galaxies could form, which stars could be born, which planets could exist. Without it, Earth might never have formed. Your atoms might never have been created. Your story might never have begun. We are children of something we cannot see, and that is both terrifying and beautiful, because it means the universe is far bigger than our senses, far stranger than our instincts, far deeper than our imagination. Dark matter reminds us of something uncomfortable. Most of reality does not care whether we understand it, but it waits quietly, patiently, for us to become curious enough to hunt it. If dark matter never touched light, how did we ever find it? The answer is simple and unsettling. We didn't see dark matter. We saw what it did in science. You don't always need to see something directly. Sometimes you only need to watch how everything else behaves around it. Wind is invisible, but you see trees bend. Gravity is invisible, but you see apples fall. Dark matter is invisible, but you see galaxies move in ways that should be impossible. The universe is constantly in motion. Stars orbit galaxies. Galaxies orbit clusters. Clusters drift through the vast cosmic web. Every movement tells a story about the forces acting behind the scenes. And when scientists began to carefully measure those movements, the story stopped making sense. Take our own galaxy. The Milky Way, it contains hundreds of billions of stars. If you calculate how much gravity all those stars produce, you can predict how fast they should orbit around the galactic center. Stars near the center should move fast. Pulled by a lot of mass, stars farther out should move slower, because there's less mass inside their orbit. That's how our solar system works. Mercury moves fast. Neptune moves slow, but galaxies refuse to follow that rule. When astronomers measured star speeds in spiral galaxies, they found something shocking. Stars far from the center were moving just as fast as stars near the middle. Their speed curve didn't fall, it stayed flat. This is called a flat rotation curve, and it shouldn't exist. If only visible matter were present, the outer stars would not have enough gravity to hold them. They should escape into intergalactic space, but they don't. They stay locked in orbit, as if wrapped inside a massive invisible halo. That halo is dark matter. This pattern appears everywhere. Not just in one galaxy, not just in a few, but in almost every spiral galaxy we have ever studied. Different sizes, different shapes. Different histories, same strange behavior. It is as if every galaxy is swimming inside a dark ocean that no telescope can see. But motion inside galaxies was only the beginning. On even larger scales, entire galaxies move in ways that reveal hidden mass. In galaxy clusters, hundreds or thousands of galaxies orbit around a common center. Their speeds are extreme, so extreme that visible matter alone cannot explain why the cluster hasn't torn itself apart. One of the strongest proofs came from something called the bullet cluster. This is not a single galaxy, but two massive clusters of galaxies that collided with each other. When they smashed together, their hot gas visible in X-rays slowed down and clumped in the middle. But the gravitational mass measured through lensing moved ahead. In other words, the visible matter stayed behind. The gravity moved forward. This means most of the mass was not in the glowing gas. It was in something invisible that passed straight through the collision. Without slowing down, that invisible mass behaved exactly like dark matter is predicted to behave. This was a turning point. The bullet cluster showed that dark matter is not just a mathematical trick. It behaves like a real substance, separate from normal matter. It can move independently. It can pass through collisions. It can dominate gravity even when invisible. Gravity also reveals dark matter through a phenomenon called gravitational lensing. Light normally travels in straight lines. But when it passes near massive objects, gravity curves space itself, and the light bends with it. Sometimes this creates beautiful arcs of light, stretched galaxies, or even multiple images of the same object. By measuring how much the light bends, scientists can calculate how much mass must be present, even if that mass is invisible. When they do this for galaxy clusters, they consistently find more mass than they can see. Far more. The lensing maps showed giant clouds of invisible matter surrounding galaxies and clusters like ghostly cocoons. This is dark matter, drawn not in light, but in gravity. Even the early universe carries dark matter's fingerprints. After the Big Bang, the universe was almost perfectly smooth. But tiny fluctuations in density existed, slightly denser regions and slightly emptier ones. Over time, gravity amplified these differences. Dense regions pulled in more matter. Voids lost matter. But normal matter alone is too slow to explain how galaxies formed so early. Dark matter, however, clumps much faster. It does not interact with light or pressure, so it collapses into structures quickly. Normal matter then falls into those structures like rain into valleys, when scientists simulate the universe with dark matter included. The results look strikingly similar to what we observe today: filaments of galaxies, giant voids, massive clusters. When they remove dark matter from the equations, the simulated universe fails. Galaxies form too slowly. Structures look wrong. The cosmic web collapses. The universe itself seems to be telling us, I was built on invisible foundations. Dark matter is not a small correction. It is not a minor detail. It shapes the universe on every scale, from galaxies to clusters to the structure of space itself. And yet, despite all this evidence, we still face an uncomfortable truth. We know how dark matter behaves. We know where it is. We know how much of it exists, but we do not know what it is. It does not fit into the particles we already know. It does not glow, collide easily, or decay into visible forms. It barely interacts with anything except gravity. It is as if nature is hiding a massive part of itself behind a one-way mirror. Every piece of evidence we gather comes indirectly. We watch stars move. We watch galaxies bend light. We watch clusters collide. We watch the universe grow. And in every case, the message is the same. There is more here than meets the eye. Dark matter is not a theory waiting for proof. It is a conclusion forced upon us by the universe's own behavior. The question is no longer, does dark matter exist? The real question is, what kind of thing can be so powerful and yet so silent? And in the next scene, the hunt becomes more personal. Because now, scientists are no longer just observing dark matter. They are trying to catch it. If dark matter shapes galaxies, bends light, and builds the cosmic web, then one question becomes impossible to ignore. Can we catch it? Not with telescopes, not with cameras, not with our eyes. To find dark matter directly, scientists must do something far more difficult. They must wait for something invisible. To touch something visible. This is not a hunt with nets or traps. This is a hunt measured in patience, silence, and years of waiting. Because if dark matter is made of particles as many, theories suggest then those particles are passing through Earth right now. Through your house, through your body, through the entire planet. They don't slow down, they don't stop, they don't care. But, in theory, once in a very long while, one of those particles might collide with an inside a detector, and that single, tiny collision would change science forever. To make that possible, scientists build experiments in the strangest places on Earth, deep underground, under mountains, inside abandoned mines, beneath kilometers of rock. Why go so deep? Because Earth's surface is loud cosmic rays crash into the atmosphere. Radiation leaks from space, from the ground, from even our own bodies. All of this creates noise signals that could hide the whisper of dark matter. So scientists go underground, where rock acts like a shield. They build chambers of liquid xenon, argon, germanium crystals, or other ultra-pure materials. They surround them with sensors so sensitive they can detect the tiniest flicker of energy. These detectors wait not for minutes, not for days, for years. One of the most famous experiments is called LUX, later upgraded to LZ. Another is XENON, buried deep under Italy's mountains. Others exist in China, Canada, and the United States. They all share the same dream: to see the invisible touch the visible. If a dark matter particle hits an atom in their detector, it should create a tiny flash of light or a small vibration. Sensors would record it. Computers would analyze it. Scientists would celebrate, but year after year, the detectors remain mostly silent. No confirmed dark matter hit. No undeniable signal to some. This is disappointing to scientists. It is information. Each failure tells them what dark matter is not. If dark matter were heavy, they should have seen it by now. If it interacted strongly, they would have detected it, so the theories change. The possibilities narrow. The hunt becomes sharper, but underground detectors are only one path. Some scientists look up instead of down. If dark matter particles can collide with each other, they might sometimes destroy each other, releasing energy in the form of gamma rays. Telescopes like Fermi and other space observatories watch the sky for strange excesses of high-energy light. They focus on places where dark matter should be dense, the center of our galaxy. Dwarf galaxies, galaxy clusters. Sometimes they see hints, strange signals. Excess radiation, but nature is tricky. Pulsars can mimic dark matter signals. Black holes can fake them. Unknown astrophysical processes can confuse the picture. Every potential discovery must survive years of testing, doubt, and debate. Dark matter does not reveal itself easily. Some scientists search in a more subtle way. They build experiments to detect exions, tiny particles that might convert into light in strong magnetic fields. They create powerful magnets and microwave cavities, hoping to catch a whisper of energy that shouldn't be there. Others use particle accelerators, like the Large Hadron Collider. They smash particles together at incredible speeds, hoping dark matter might be created in the collision. They cannot see dark matter directly, but they can see energy go missing. If a collision produces particles that vanish without a trace, something invisible may have carried that energy away. So far, no confirmed dark matter particle has appeared. But this is not failure. This is exploration. Science often advances through what does not happen. Every empty result tightens the map of the unknown. Meanwhile, dark matter continues to shape the universe effortlessly while we struggle to even touch it. And this raises a deeper question. What if dark matter is not a particle at all? What if it is something stranger? Some scientists suggest that gravity itself might behave differently over vast distances. Maybe our equations, tested in the solar system, break down on cosmic scales. This idea is called modified gravity. Instead of adding invisible matter, it changes the rules of gravity. But modified gravity struggles to explain everything at once. It can fit some galaxy data, but fails with galaxy clusters. Lensing and the early universe dark matter still explains. More with fewer changes. But the debate continues. And that is what makes this hunt powerful. This is not just about finding a particle. This is about questioning the foundation of physics. Every experiment asks, do we understand gravity? Do we understand matter? Do we understand the universe at all? Dark matter stands like a locked door in the middle of modern science. On one side, everything we know, stars, atoms, light. Life on the other side, something massive, silent, and invisible, and we don't yet have the key. But history tells us something important every time. Humanity thought reality was complete. It wasn't. We once thought atoms were indivisible. We once thought time was absolute. We once thought space was empty. Each time, nature proved us wrong. Dark matter is likely another step in that story, a reminder that the universe is not designed to be easily understood, but we keep asking, we keep building, we keep waiting, because somewhere in the darkness, something real is moving through us, unseen, unknown, and patient, and we are determined to meet it. To truly understand dark matter, you have to stop thinking small. Not planets, not stars, not even single galaxies. You have to think in structures so large they take light billions of years to cross, on the biggest scale possible. The universe is not random. It is not evenly filled. It is not chaotic. It has a shape. When astronomers map millions of galaxies, they see a strange pattern. Long threads of galaxies stretching across space, intersecting in massive knots, surrounding enormous, empty regions called voids. This is called the cosmic web. It looks like a spider web, made of galaxies' filaments glowing faintly, tracing an invisible skeleton. And that skeleton is made of dark matter in the early universe. Shortly after the Big Bang, matter was spread almost evenly, but not perfectly. Tiny differences in density existed. Some places had a little more mass than others. Those tiny differences mattered. Dark matter, because it doesn't interact with light or pressure, began collapsing into clumps very quickly. Normal matter, however, was tied to radiation and heat. It couldn't collapse easily at first, so dark matter moved first. It formed invisible hills and valleys in space gravitational landscapes. Later, when the universe cooled, normal matter fell into those valleys. Gas gathered. Stars ignited. Galaxies were born where dark matter already waited. This means galaxies are not the architects of the universe. They are decorations placed on a structure they did not build. Simulations show this clearly. When scientists create virtual universes using supercomputers, they include gravity, expansion, and dark matter. They let the simulation evolve. When dark matter is included, the result looks eerily like our real universe: filaments, clusters, voids, and galaxy chains. When dark matter is removed, the universe looks wrong. Structures form too slowly. Patterns don't match what telescopes see. The web collapses. The universe itself seems to demand dark matter as part of its design. Dark matter also explains something deeply important: time without dark matter. galaxies would have formed too late. The universe is only about 13.8 billion years old. Without dark matter, there simply wouldn't have been enough time for gravity alone to pull normal matter into galaxies so early dark. Matter speeds up structure formation. It acts like scaffolding, around which the visible universe grows. This invisible architecture controls where matter flows, where galaxies collide, where clusters grow. And where emptiness remains, even empty space is shaped by dark matter. The giant voids between galaxy filaments are not random gaps. They are regions where dark matter density is low. Matter flows away from them toward denser regions. The universe is slowly draining itself into invisible valleys. Dark matter also shapes galaxy behavior from the inside. Each galaxy sits inside a massive halo of dark matter much larger than the visible galaxy itself. This halo stabilizes the galaxy, holding stars in place, guiding their orbits. Without that halo, spiral galaxies might never exist in their beautiful shapes. They would be unstable, distorted, or torn apart by interactions. Dark matter gives galaxies memory. It remembers past collisions. It stores gravitational history. When galaxies merge, their dark matter halos merge first silently, invisibly guiding the future shape of the combined system. In galaxy clusters, dark matter dominates completely. Most of the cluster's mass is invisible. The glowing gas and stars are just a small fraction, floating inside a much larger dark sea. When clusters collide, like in the Bullet cluster, dark matter halos pass through each other almost untouched while gas crashes, heats up, and slows down. This shows something strange about dark matter. It behaves like matter, but without friction. Normal matter collides, sticks, heats up. Dark matter simply passes through itself and everything else, guided only by gravity. This makes it perfect for building large structures. It clumps, but doesn't collapse into stars. It gathers, but doesn't shine. It shapes, but does not reveal itself. It is architecture without decoration. Some scientists call it the universe's dark backbone. But here is the unsettling part. We understand the shape of this backbone better than we understand its substance. We can map dark matter through lensing. We can simulate its behavior. We can calculate its influence, but we cannot hold it. We cannot photograph it. We cannot name its true form. We are studying a skeleton we cannot touch. This forces us to confront a strange idea. Most of reality is not made of what we can see. Our senses evolved to understand a tiny, warm, bright corner of the universe. But the universe itself is cold, dark, and silent. Dark matter belongs to that deeper reality. It reminds us that light is not the main story. It is just a surface effect. And as we map more of the cosmic web, as we trace more invisible filaments, one truth becomes clear. We are living inside a structure built by something we do not yet understand. And in the next scene, the hunt turns inward toward theories, debates, and the possibility that we may need to rewrite physics itself to explain what we are seeing. At some point in every great mystery, the question changes. It stops being, "Is this real?" and becomes, "What is it made of?" By now, dark matter has passed the test of reality. Too many observations depend on it. Too many cosmic behaviors collapse without it, so the hunt becomes more specific. If dark matter exists, what is it? We know what it is not. It is not stars, because stars shine. It is not planets. Because planets reflect light, it is not gas or dust. Because those block or glow in radiation, it is not black holes in large enough numbers. Because we would see their effects in other ways, Dark matter does not interact with light in any normal way, so scientists turn to the smallest things they know: particles. The standard model of particle physics describes all known particles: electrons, quarks, neutrinos, photons. But none of these can explain dark matter. Neutrinos come close. They are nearly invisible, barely interacting. But they are too light and too fast. They cannot clump into the structures we see, so dark matter must be something new. One popular candidate is called WIMPs, weakly interacting massive particles. These hypothetical particles would be heavy, much heavier than protons, and would interact only through gravity and the weak nuclear force. They would rarely touch normal matter, making them almost impossible to detect. WIMPs fit nicely into some theories beyond the standard model, like supersymmetry. For years, they were the leading idea, but as experiments fail to find them, confidence slowly fades. Another candidate is exions. Exions would be incredibly light, far lighter than electrons, but they could exist in enormous numbers. Together, they could account for dark matter's mass. Ixions have strange properties. In strong magnetic fields, they might turn into photons, particles of light. This gives scientists a way to open them. Experiments like a DMX use powerful magnets and ultra-sensitive detectors to listen for faint radio signals that might come from exions turning into light. So far, no confirmed detection. But the search continues. Some theories suggest dark matter might be made of sterile neutrinos particles similar to normal neutrinos, but even more ghost-like. They would barely interact with anything, except through gravity. Others propose dark matter could be made of multiple types of particles, a whole dark sector, with its own forces, its own interactions, and its own hidden complexity. Imagine a shadow universe layered on top of ours, interacting with us only through gravity. That idea sounds like science fiction, but mathematically, it is possible dark matter might not be simple. It might have families of particles. It might have forces we cannot feel. It might even have structures of its own. But how do you test something that refuses to interact? You try everything. You smash particles together in accelerators, hoping dark matter will appear and escape. You build detectors underground, hoping dark matter will bump into an atom. You watch space for strange radiation. You simulate the universe and compare it to reality. Each method is like casting a net into darkness, hoping something invisible will ripple the surface. But maybe the problem is deeper. Maybe dark matter is not made of particles at all. Some scientists argue that gravity itself might be incomplete, that on very large scales. It behaves differently from what Einstein predicted. This idea is called modified gravity, instead of adding invisible matter. Modified gravity changes the rules of how gravity works when distances become enormous. These theories can explain some galaxy behaviors, but struggle with others, like lensing and galaxy clusters. They often need fine-tuning. Dark matter still fits more observations more naturally, but the fact that such ideas exist shows how serious the mystery is. When scientists are willing to rewrite gravity itself, you know the problem is deep. Dark matter is not just a missing ingredient. It is a stress test for physics. It pushes our theories to their limits. It exposes what we don't understand. It forces new ideas to be born. Every candidate for dark matter is also a candidate for new physics. Finding dark matter would not just explain galaxies, it would change particle physics. It would reshape cosmology. It would open a new chapter of science. But there is a quiet fear behind the hunt. What if dark matter is so different that our current tools can never touch it? What if it interacts only through gravity and nothing else? If that is true, direct detection might be impossible. We may never catch dark matter in a lab. We may only ever know it By its shadow. But even shadows tell stories. They tell us something is there. They tell us how big it is. They tell us how it moves. And sometimes, knowing how something moves is enough to understand what it is. Dark matter is teaching us patience. It does not reveal itself quickly. It does not reward shortcuts. It does not care about our expectations. It exists on cosmic timescales. It demands cosmic patience. And as we search for its substance, we are forced to look deeper, not just into space, but into the foundations of reality. Because whatever dark matter is, it is not just missing matter, it is missing understanding. Every great scientific mystery reaches a moment when confidence cracks, when even the strongest explanation is no longer taken for granted. Dark matter has explained galaxies, clusters, lensing, and the cosmic web. But its very invisibility creates a dangerous question. What if we are wrong? Not about the observations, but about the interpretation. Maybe there is no invisible matter at all. Maybe gravity itself behaves differently when distances become enormous. This idea is not new. In the past, when Mercury's orbit didn't match predictions, scientists didn't invent invisible planets. They changed gravity itself, leading to Einstein's theory of relativity. So it is fair to ask, is dark matter a new substance? Or a sign that gravity needs to be rewritten? Some scientists propose theories called modified Newtonian dynamics, or MOND. These ideas change how gravity behaves when accelerations become extremely small, like in the outskirts of galaxies. MOND can explain flat galaxy rotation curves without dark matter. That is impressive. But MOND struggles with galaxy clusters, gravitational lensing, and the early universe. It fixes one problem by breaking others. More advanced theories try to combine modified gravity with Einstein's equations. They introduce extra fields, extra dimensions, or new mathematical structures. But every change must match a universe full of data. Cosmic background radiation, galaxy distribution, lensing maps, and expansion history so far. Dark matter, despite being invisible, fits. More evidence, more cleanly. But the doubt remains, and that doubt is healthy, because science does not exist to defend its favorite ideas. It exists to destroy them if reality demands it. Dark matter is not sacred. It is provisional if a better explanation appears. Dark matter will be replaced without regret, but right now, it still stands another kind of doubt comes from silence. Decades of experiments, billions of dollars, thousands of scientists, and still no confirmed dark matter particle. That silence is unsettling. Is dark matter hiding? Or is it not what we think it is? This has led some scientists to imagine more radical ideas. What if dark matter is not a particle, but a property of space itself? What if space has hidden structure that affects gravity? What if the vacuum is not empty, but active? These ideas are difficult to test, but they show how far the mystery reaches. Dark matter is no longer just an astronomical problem. It is a philosophical one. It asks, what does it mean for something to exist? Does existence require interaction? Can something be real if it never touches us? Dark matter forces us to confront the limits of observation. We only know what we can measure. We only measure what interacts. We only interact with what allows it. If most of the universe refuses to interact with us, then most of the universe will always remain hidden. This is not failure. It is humility. Science is powerful, but not omnipotent. Dark matter reminds us that nature does not owe us clarity. We explore not because answers are guaranteed, but because mystery itself is worth chasing, and whether dark matter turns out to be particles, modified gravity, or something no one has imagined yet, one thing is already true. The hunt has changed us. It has forced collaboration between astronomers, particle physicists, cosmologists, and philosophers. It has driven new technology. It has expanded our idea of what reality might be, even if dark matter is never directly seen. It will have shaped science forever, and in the final scene, the story becomes personal, because dark matter is not just out there, it is passing through you, right now. Every second of your life, something unseen is passing through you. Not metaphorically, literally, right now, while you breathe. While you listen, while you exist, countless dark matter particles, or whatever dark matter truly is, are flowing through your body like a silent cosmic wind. They do not touch your skin. They do not feel your bones. They do not change your thoughts. They pass through you, as if you are made of empty space, and in a way, you are. Atoms are mostly emptiness. Matter is mostly void, and dark matter moves through that void without resistance. This is not science fiction. This is what the equations say. If dark matter fills our galaxy the way models suggest, then trillions of dark matter particles cross your body every second. You are living inside a storm you cannot feel, and yet without that storm, you might never have existed. Dark matter shaped the galaxy that formed our sun. It guided the gas that became Earth. It built the gravitational environment that allowed life to arise. Your atoms were forged in stars. Those stars were placed by dark matter, so in a deep sense, dark matter is part of your origin story, not in your blood, not in your DNA, but in the cosmic path that made you. Possible, we often think of ourselves as separate from the universe. But the universe is not outside us, it is inside us. Literally, every atom in your body was once inside a star. Every star was guided by gravity. Every gravitational structure was shaped by dark matter. You are the visible result of invisible forces. This changes how you look at reality. It means what you see is not the full story. It means what you touch is not the whole truth. It means existence is deeper than appearance. Dark matter is not just a scientific problem, it is a reminder that the universe is not built for our senses, that reality does not care what we can see, that truth does not require light, and yet, despite this, we keep trying. We build machines under mountains. We send telescopes into space. We write equations that stretch the mind, not because we are guaranteed answers, but because we are curious, because we are human. The hunt for dark matter is not just a hunt for particles, it is a hunt for understanding. A hunt to know what kind of universe we live in, what kind of laws rule it, what kind of place could create beings who ask questions about their own origins, and maybe one day, someone will find it. A single flash in a detector, a strange signal from space, a missing piece in an equation, and the invisible will become visible not to the eye, but to the mind. Until then, dark matter remains what it has always been. Silent, massive, unseen, but not unknown, because even in darkness, we are learning how to see.